we have a stereo pair, an image that corresponds to the left eye and an image that corresponds to the right eye, if we can come up with a mechanism for directing those two slightly different images to the respective eyes, then we have a very, very vivid sense of the three-dimensionality of the scene. And this is the underlying principle of 3D movies, 3D television, and so on. And it's something human beings have been fascinated with for the longest time. I really love this movie poster in this scene from a cinema back in the 1950s. It shows us that there's this long-term human fascination with 3D movies. It's not a recent phenomena. The technology keeps changing, but the underlying principle is exactly the same. The fundamental problem we need to address is how do we get different image into our left eye and our right eye. Let's have a look at some of the technologies that have been developed over the years. In order to reproduce the really vivid 3D perception we get in everyday life, we need to use some rather elaborate mechanisms to recreate that effect artificially. So the first one is back from probably early last century. And what this device does is takes an image which corresponds to an image from the left eye, another image which is taken from a position that corresponds to the right eye. And then this lens mechanism here sends the left image into my left eye and the right image into my right eye. So if I hold this up to my face, I see a really vivid three-dimensional representation of the scene that was captured, more than 100 years ago. So this is the first kind of stereoscope, and these things were really, really popular in the early 1900s. So a slightly more modern version of that technology is something from the 1960s, and this one has a number of stereo image pairs on a little piece of cardboard and a little clicker, so I can move from one picture to the other much more conveniently. And if I hold this up to my head, again I get a very vivid 3D perception of the scene that I'm looking at. Another approach to providing different images into the left and right hand eye is what's called the anaglyph technique. And you look at an anaglyph image through red and blue glasses. And what happens is that the left image is printed in red and the right hand image is printed in blue. And by putting on these filtered glasses, the left hand image comes through the red filter into my left eye. It does not pass through the blue filter, so my right eye doesn't see that. And for the right hand image, the one that's printed in blue, comes through the blue filter into my right eye, but not into my left eye. So if I put this on and look at a printed anaglyph image or an anaglyph image on a web page, for instance, NASA have got lots of anaglyph images of Mars, we get a very, very vivid 3D sensation. This is just one image from NASA's collection of 3D anaglyph images. The most recent Mars rovers all carry quite sophisticated stereo vision systems, and the images are transmitted back to Earth, processed by NASA and turned into anaglyph form and made available through their website. What we don't get, though, is a very full representation of the color because we're looking at it through red and blue glasses. So it looks a bit monochromatic, but the 3D perception is really quite vivid. If you've got access to a pair of anaglyph glasses, these are glasses with the red and blue lenses, you might be interested to grab them, put them on and have a look at these next few images. They contain some very vivid three-dimensional content. The toolbox function that draws 3D coordinate frames has an anaglyph mode. If we call the trplot function, which we've seen before, and pass in a rotation of 90 degrees around the x-axis, so that's the coordinate frame that we want to display. And we pass the 3D plot option. And if I view this through my anaglyph glasses, I get a very realistic 3D impression. I actually see that z-axis coming out of the screen somewhat. Another technique, and the one you see in 3D movies, you can see Gravity or Avatar, The Hobbit, something like that, you put it on glasses like this. And what happens in the theatre is that the left-hand image is projected with light that's polarized, perhaps in the vertical direction. And that light goes through this filter, which lets through vertically polarized light into my right eye, but not into my left eye because this filter is polarized in the horizontal direction. Similarly, if the right-hand image is projected with a vertical polarization, comes through this filter, but not into this filter. So when I put this on my head in the cinema, I see a really wonderful 3D, colorful representation of the scene that was filmed. For home use with three-dimensional TVs, the technology is a little bit different, and what we use are these liquid crystal shutter glasses. And what happens now is that the television presents the left and right images sequentially, about 100 times per second. We have the left image, right image, left image, right image. And the lenses in these glasses are synchronized with the TV. So when the left image is projected, this lens becomes clear, and this one is opaque. So I only see the left image in my left eye. Then 100th of a second later, the right image is projected on the TV. This lens goes black and this one goes clear. So with these in my head, I get a very vivid, again, colorful and three-dimensional representation of the scene through the TV. The final approach is to do away with trying to use colored glasses, filtered glasses, shuttered glasses on my head, and to project the left and the right image directly into my eyes. So in some ways, that's a high-tech analog of the old stereoscopic viewers like this one and this one. So here is a state-of-the-art head-mounted display. If I put this on my head, the left image is projected through this lens directly into my left eye, and the right-hand image projected through this lens directly into my right eye. All of the techniques that we've looked at require us to wear something on our head, and that's not always very convenient. Maybe we don't have the particular glasses to hand, or maybe we find that it gets in the way of our everyday life. So there's been quite a bit of work in trying to create the stereo effect without needing to have anything on your head. So one fairly recent innovation is the technology shown diagrammatically here. It requires that your head is approximately the right distance away from the screen, and there is a system of lenses which refract the light from the left-hand image in the general direction of your left eye, and the right-hand image is refracted in the general direction of your right eye.